Now let's work through a parallel circuit sample. So here we're going to apply an AC signal to 3 parallel components. So we have a resistor, a 3.33 ohm resistor, a 1.43 ohm inductor. Okay, so when you're given ohms for the inductor and the capacitor, that means they've already found the reactance for you. So if you had henries for the inductor, you would have to find the reactance first. And same thing for the capacitor. So just keep in mind that since you were already given the reactance first, we don't have to find the reactance. So we're already given that information. Okay, so the first thing we do want to do is find the phasor voltage because, again, we were given the time varying sinusoidal equation. So we're going to need to find the phasor voltage first. So here we did that. We multiplied 0.707 times the peak voltage of 70.7 to find the RMS voltage. And that's what we're using in our phasor voltage. We're using the RMS voltage and the phase shift for the voltage, which is 0 in this case. Next, we need to find the impedances of each of our components. So for ZR, that's just going to be the resistor value at 0 degrees. So we've got 3.33 at 0 degrees. For the impedance of the inductor, we're going to take the reactance of the inductor at 90 degrees. So that would give us 1.43 ohms at 90 degrees. And for the impedance of the capacitor, that should be C right there. We're going to call it C. For the impedance of the capacitor, we're just going to take the reactance of the capacitor at negative 90 degrees because it's a capacitor. So Z sub C would be 3.33 at negative 90 degrees, and there we have the impedance of all 3 of our components of our circuit. To find the total impedance of the circuit, we're actually adding the admittance, and actually those should be Y. Admittance is Y. So if you're using the calculator, you can use either the polar or rectangular forms of the impedance. I actually think it's easier to enter the impedance in this case. I think it's easier sometimes in rectangular form, but you can use either form. So remember, for the resistor, the impedance is 3.33 at 0 degrees. Well, in rectangular form, that's just 3.33 plus 0J. But we can leave out the 0J. Okay, we don't need that in our equation, so that'll just make things a little easier. For the impedance of the inductor, we have 1.43 at a positive 90 degrees, which is 0 plus 1.43J in rectangular form. And again, since the X portion is 0, we can leave that off as well. And then the impedance for the capacitor is 3.33 at negative 90 degrees, which would be 0 minus 3.33J in rectangular form. And again, since the X portion is 0, we can leave that off. And I think I got rid of my negative. We do have to keep the negative sign there. So if I were to put this into my calculator, here's how I would do this. Remember, this is how you combine parallel resistors. We're going to do the same thing for AC with our impedances. The only difference is these are complex numbers that we're working with. That's the only difference. So here's how I would enter this. So I would take my resistor, 3.33, and raise it to the negative 1. So if you have an X to the minus 1 button, you might use that to do that. Or if you have a 1 over X button, you would use that. Both will accomplish this for you. Or you can, after you type the 3.33, you can do the hat negative -1. And that will also accomplish that for you, either of those three ways. Okay, so I would type 3.33 times to the -1 plus my 1.43j to the -1, and put those in parentheses, plus my -3.33j for the capacitor to the -1. Then I would hit enter, and then raise this to the -1 again, and hit enter again. And that should give you your total impedance of 2 at 53.13 degrees. If it gives you that in rectangular form, you might want to convert it to polar form so that we can then apply Ohm's law. And we apply Ohm's law to find our source current, just like we've learned to do so many times before. So here is our Ohm's law, and for AC we would just take our source voltage in phasor form, the 50 at 0 degrees, and divide by ZT, which we just found was 2 at 53.13 degrees. To do the math, 50 divided by 2 gives us the magnitude of our current, 25 amps, and 0 minus 53.13 degrees gives us the phase shift for that current. Okay, so that's what we have there. Now, let's go back up here and write that into our circuit. Okay, so that tells us that we have coming from the source 25 amperes at -53.13 degrees. That's I sub S. Now, this is a parallel circuit, and if you remember from DC, components in parallel have the same voltage across them. So what we're going to look for now is the current through each of these branches of our circuit. So we know that the phasor voltage that we found here is going to be the same. We know that that phasor voltage is going to be the voltage across our resistor, the voltage across our inductor, and the voltage across our capacitor. So we're going to apply that using Ohm's law to find the current through each. Okay, so for the current through the resistor, we're just going to take our source voltage in phasor form, 50 at 0 degrees, and divide by our resistor impedance, 3.33 at 0 degrees. 50 divided by 3 1/3 gives us a current of 15. 0 minus 0 degrees gives us 0 degrees for our resulting current phase shift. For the inductor, same thing. Our phasor voltage, 50 at 0 degrees, divided by our inductor impedance, 1.43 at 90 degrees. 50 divided by 1.43 gives us 35 as our magnitude, or length of that vector. 0 minus 90 degrees gives us a -90 degree phase shift for I sub L. And then for our capacitor, our phasor voltage divided by the capacitor impedance gives us 15 at 90 degrees. You should be able to plug these into your calculator to see that I sub S does indeed equal IR, IL plus IC. Okay, so you can, again, do some practicing with your calculator, and if you need help with that, look back to some previous videos for that. And that is how we would work through a parallel circuit in AC.